separate the sharing. If it's green, does that mean it's currently sharing? Or you are?
Yeah, that's me.
Yeah, okay, good. So Sean Tull is going to talk about active inference in string diagrams. So off you go.
All right, can everyone hear me okay? Yeah. Thanks so much. Thanks to the organizers for a wonderful conference and the chance to speak to you all. So I'm going to be talking about how we can use string diagrams to study a framework in cognitive science for studying cognition, known as active inference and also predictive processing. And I'll just say, yeah, this is joint work with Johannes Kleiner and Toby St. Clair-Smythe, who's probably here. Yeah. It was carried out as on a FQXI project that was hosted at the Topos Institute, so we're very grateful to them. And yeah, I'd like to thank Continuum as well for giving me time to work on this. So I will be talking about these frameworks. A framework known as predictive processing, which is a model of cognition that aims to be something you can apply in a principled way, say to a whole organism or down to a single neuron, so sort of operating at all levels. And they can be distinguished for the purposes of this talk. I'll just be equating it with this variant known as active inference that's been developed by Carl Friston and his collaborators. So I'll kind of end up using the terms interchangeably here. And the key idea in the approach is that an agent comes with a generative model that they use to explain the observations they receive from the world in terms of some hidden states and their own actions. So when they receive these observations, they want to make sense of them in terms of these representations. So when they see these observations, they want to get hidden states out of those. That's called perception. And they also want to plan their actions. And in active inference, both of these are done through a kind of approximate Bayesian inference by minimizing this quantity known as free energy. So we'll talk about all this stuff as the talk goes on. And so, yeah, it aims to be a very principled account of cognition, but it can still be quite a lot of work to make it through the active inference literature. So we kind of wanted to give a nice, concise formulation of the theory that would be useful to mathematicians. And we use category theory to do so. And the reason that you might want to take a categorical approach, other than that, is that it tends to be very compositional in the way that it works, active inference. So the generative models that these agents have are very compositional in their nature. They're often these so-called hierarchical models. And you can basically see them as like the causal models that I talked about in my causal model talk on Thursday. So we can, in particular, I'll just be using the same formal setup there to describe the generative models, essentially. And just on related work, because it's about intelligence and it's built from these compositional models, you can see this is a kind of biological variant of this compositional intelligence that we're interested in studying at Continuum, which just kind of means categorical kinds of models of intelligence. And it's also related to, there's lots of work on these kind of topics going on in ACT. In particular, a lot of them are classed under what's called categorical cybernetics. So the setup is going to be a familiar one by now, I think, to most people at the conference. So we're working in CD categories. So that's symmetric model category with copying and discarding maps, reading my diagrams bottom to top. And again, we'll just need to really think about the finite discrete settings fine here. So we'll be working in MATR+, where the objects are just finite sets, and a morphism M running up from X to Y like this would be given by specifying a positive real for each input X and output Y. Now we compose them sequentially, matrix multiplication and in parallel with a tensor. And exactly the same as in my other talk, we often want to pick out the ones that really do correspond to probabilistic maps, which are called channels. They're often called total as well. So those are the ones that preserve discarding. And again, for states, this means that the state is normalized, so it corresponds to a probability distribution. More generally, the channels would correspond to probability channels in the usual sense. And we'll obviously talk about marginalizing things a lot, where we plug the discarding in on an output. So yeah, as I mentioned, the key idea is that the agent has one of these generative models that's relating their observations with actions they can perform and their model of the world. Normally, this has a lot of compositional structure to it, so it's given by a Bayesian network. You can see it as a causal model, really, because the model basically says that the observations are being caused by these hidden states, like they're a causal explanation for what's going on. So we can use this setup of causal models. The standard way is to model one of these with a DAG and a load of probability channels, but we can also nicely treat them in string diagrams, as we will. And I've just here mentioned that in the active inference literature, I feel like they're kind of converging on string diagrams independently. So they if you were just drawing a DAG, you can only get to label the objects, as it were, not really the channels. But they clearly like that you can label both, like you can with string diagrams, and so that their diagrams can just be immediately turned into the kind of diagrams we're using a lot of the time. So to describe these Bayesian networks, you normally start from a DAG, and just as before, there's a known correspondence between these DAGs and a certain class of string diagrams that we'll call network diagrams. So remember, this just means that it's a string diagram that's built from copying, discarding, and boxes with one output and multiple inputs. So given any one of these DAGs, you can construct an equivalent network diagram, and the only other thing you specify is which some of your DAGs you consider to be outputs. So these are like the observed variables in your model, and the rest would be hidden. So on the bottom here, we have the DAG, same pictures from the Causal Models talk. You have this DAG and the equivalent network diagram. So x2 and x3 here are circled. They'd be like observed variables, and the other two would be hidden. And so in the network diagram, you take a wire for each variable, and you copy it. You have a box that produces that wire. So like the box C is producing x2 here in terms of its parents in the DAG, so that's x1 and x4. And you pass it to its children in the DAG, and you pass it out of the diagram as well if it's an output. So to give a causal model of one of these, just meant to interpret one of these diagrams in a particular CD category. So to give a causal Bayesian network basically of this form, you would just have to actually say what the sets are for all the wires and what the probability channels are for all the boxes. So in this work, we call these things generative models, but formally they're just the same as how I define open causal models if you saw that talk. And the only extra ingredient is this open idea. So ignoring the word open for now. So a generative model in a CD category C, it's the same as just a causal model with an interpretation of being possessed by an agent. And what does the causal model bit mean? It means it's one of these network diagrams along with this interpretation. So you say what the actual sets are, what the objects are for the wires, and what the channels are for the boxes. And the open part here refers to how we allow not just network diagrams with no inputs, that was on the previous slide, but now we allow our network diagrams to actually have potential inputs as well. So this diagram here would show the structure of an open generative model now, where x2 and x3 are the inputs, and x3 is also an output, and x5 is an output. x1 and x4 are hidden or internal variables. And so to give a causal model of this form, you just give these channels A, B, C, and you give all the objects for the wires in your CD category. I will call them closed when they don't have any inputs. If you take in our example category MATR+, this is just one of these causal Bayesian networks, except we kind of allow optional inputs. So like x2 and x3 don't have any channels specified, they're just inputs to the whole system. So that's the formal setup. Now let's just see like the kinds of generative models that actually appear in predictive processing. The simplest thing is just literally this network diagram. We just have one object of hidden states, one object O of observations, and it just says that the states cause the observations. So that means S has no parent, so it's just got this prior distribution over it, and it has this channel that's often called the likelihood going from your hidden states to your observations. And you often study this thing by looking at the induced distribution over both variables. So this would be given by just kind of declaring S to be not hidden anymore, if you like. So then you'd obtain this network diagram. If you interpret that as a distribution, it's like the one with this density here. So in a sense, this is like the archetypal generative model, just showing the hidden states and the observations. As I've mentioned, the ones actually used a lot in active inference, say, are often much more compositional. So let's walk through one. So if you read this book on active inference, for example, this is sort of the generic kind of model they always use for examples. So it's working in discrete time. So what's going on is we have n time steps here, running 1, 2, up to n. At each time step, we get some observations, like O2, let's say. So that's received as a channel from the hidden state, S2. So for example, this could be like an agent's model where the observations are what's hitting their eye, as it were, like the pixels, if you like, and the S is their internal representation of what object it is they're seeing. So you have that running for n time steps. And the model shows that the state is evolving over time with these transition channels B. So it's saying at each time the state is evolving based on the state of the previous time. But also this extra variable I haven't mentioned yet called P here at the bottom. And P stands for policies. And policy is like an action policy. So this is the behavior of the agent. So this is their model of their own behavior. So the idea is that they would, for any given policy here, they'd be acting that out, and that would influence the evolution of the state over all these time steps. And finally, yeah, there's a prior over the policies, which would describe their sort of typical behaviors. It's often called their habits. So these are the ways that they expect to act as a default. Yeah, sure.
Why are the observations complex process when you describe it?
Oh, I see. Thanks. Yeah, there'll be, in a sense, inputs to the kind of inference process that we'll get to now. But yeah, the outputs in the sense of the generative model of what's going on. Yeah.
They're the predicted outcome.
Yeah.
Forecasting.
Yeah, this is like a prediction. Yeah, if you plug this all together, distribution is what they expect to see. Exactly. Yeah. Thanks. As I mentioned a bit at the beginning, so the other thing that's very natural to treat with the diagrams is what are called these hierarchical models. So in predictive processing, you often imagine models being plugged together, and that's really natural to treat from this open generative model kind of framework. So you can imagine these kind of hierarchical models where, a bit confusingly because of the way we're reading diagrams, you'd actually have the sort of high-level variables at the bottom and the low-level variables at the top, but you would have things like more abstract things here, like an object at the bottom causing ultimately like individual receptors or something being, at the top of the diagram, or you could have different time levels running here. So having just talked about the different kinds of generative models you get, let's actually talk about what you do with them now. And the main thing it's all about is updating. This is our kind of backwards process. So say we'll just talk about having one of these simple models of some hidden states and some observations, and we get, it gives us this joint distribution over what we expect in terms of hidden states and possible observations O. And now let's say we receive a new observation. So in general, this could be a soft one, meaning it's given by distribution in this bold font O over O. And our model would normally give us a prior over our hidden states, which we could get by just marginalizing this joint distribution. And we want to update that now to our sort of posterior. So this is telling us, before we had some idea about which hidden states were likely according to our model, but now we've got this new observation. We want to update that to say which ones are likely, given that we've received this new information. Or if this observation O was sharp, so it's just like a point state, as it were, like a point distribution at one element of O, there's kind of a standard answer for what you should do here. And that's given by this sort of just conditional or Bayesian conditioning. So what you would do is take your sharp state here. You can view it in either of these two ways, but this notation here is depicting the Bayesian inverse partial channel, which you could compute from your model. So take O, and using these caps that exist in MADR+, you can bend that to make it an input, and this dash box denotes normalization for those who saw me using this in my previous talk. So this whole morphism here is the way of constructing the Bayesian inverse channel from O to S that you plug in. So this gives you the Bayesian conditional here. Equivalently, because of the way these normalization works, you could pull it in and view O as this effect, which is just equal to this cap with the O state plugged into it. So that's what you would like to do ideally in the sharp case. If you have a soft observation, though, these two pictures you basically don't have an equality anymore between these two ways of doing it. So as we saw in Elena's talk on partial Markov categories, there's these two types of updating for soft observation. The Bart Jacobs has talked about as well, called the Jeffrey style and the Pearl style updating. So in the one case, in the Jeffrey style, you compute this Bayesian inverse channel and plug your soft observation just into it as a distribution. In the Pearl style, instead, you kind of treat it as an effect. So this would be like taking the density of O, or just plugging it into that cap, and then you normalize. So they differ in where you apply this blue normalization box. And what was on the previous slide was saying, but they coincide if it was in fact sharp. So there's these two ways that you could imagine updating with soft observations. And it's sort of open, I think, like which of these is the most natural to consider in the context of cognition, or what the brain is doing. We'll actually meet a third way of updating, though, in a second. The real problem is that both of these are supposed to be computationally just intractable, so it's not really believed to be plausible that a biological agent is actually computing these kinds of updates, or even in the sharp case, doing this Bayesian inversion exactly. So in active inference, you want to approximate this whole updating process in some way. And that's why we're using this quantity called free energy, which I'll just talk a little bit about now. To treat it in terms of diagrams, we introduce this certain notation here that we call these log boxes. So let's say we have a function from our set x into the positive reals. So that would look like this effect E. And if we draw this green square around it, I hope that's big enough, this denotes now this new function given by x mapping to minus log E of x. So if E is the density of a state, this is called the surprise with respect to that state. And the reason we introduce this is because free energy is one of these quantities, as Toby was talking about in his talk, that's defined in terms of these surprises, these minus log type quantities. The given two generative models, given two joint distributions is all they really have to be, but we imagine them as arising from some generative models. So Q and M here are two joint distributions over S and O. We define this general notion of the free energy quantity like this. So you can either do it with this log box style notation, where you turn M into an effect, so that's like taking the density of M as it were, and then applying this log box. Or you could just write it in conventional probability notation here, so these two things are equivalent. So when we're plugging the state in, this is like taking an expectation value with respect to that state. So this is a general notion of free energy. The one that's most important is this sort of special case called the variation of free energy, which is used all the time. So in this case, what we're doing is we have a model M of our hidden states and observations. And like we were saying for the updating, we receive one of these specific soft observation O given by this distribution. It could be sharp as well, and this would still be worth looking at. It'd still be used. And we're now wanting to approximate those kind of Bayesian updates we were looking at. So this Q is a new distribution over S that we're trying to use to calculate our updated beliefs about the hidden states. So for any candidate Q, we can calculate this VFE quantity here. And it's just a special case of the above where this capital Q is just given by this product of our new update, the little q, and this observation. So the point of this variation of free energy quantity is it's supposed to be more tractable to calculate than full Bayesian inversions. And it has the property that if you minimize it, so you find the q which has the minimal value of this VFE, you'll get something that, so if your observation was sharp, you'd get the exact Bayesian inverse. If you're dealing with a soft observation, you'll get something else. So it's actually, we're saying we can treat this as a new third type of updating, in fact. So we define the, given an observation, this new third kind of updating, along with the Pearl and Jeffrey, we call the VFE update. So that's, you find the Q that minimizes this quantity with respect to your observation, and that is the VFE update. So we imagine that when an agent is doing its inference, it's doing this process of minimizing this VFE and carrying out these updates. I'll just quickly talk about something else we mentioned about free energy in the paper, which is this claim for how you can see it as a compositional property, and it's quite close to what Toby mentioned in his talk, I think, actually, with this copy composition and so on. So we give this new definition for how to basically extend what was on the previous slide for VFE of a closed model to one with an inputs now. So the difference is that we have this input I, also features in Q, to define like one quantity, which we just calling the open VFE, that you can now apply to an open model. And the reason we want a version of VFE for an open model is so we can talk about how VFE behaves when you're plugging different models together. The idea being that the claim of this free energy principle that's used in active inference is that you see an agent as just always aiming to do this free energy minimization. So you're kind of claiming that the whole brain is doing it and each neuron is doing it, perhaps. So that kind of only makes sense if free energy of a larger system can be minimized by the smaller parts, all minimizing their free energy as well. And that's what we're trying to establish. So for that, we define this open VFE quantity, and then we show some properties saying that it does respect composition in a suitable sense. I think I only have time to sort of sketch the way they work here. But for example, if you take two models running in parallel, it shouldn't be too surprising that the VFEs are just completely independent, so they're given by summing the two individual VFEs. So what this is saying, is that if this is our open model, from I1, it's from these joint inputs I1, I2 to O1, O2, but it just happens to be given as a tensor of two models. And the Q's and the O's are all just independent as well. Then the total VFE is just given by their sum, so that's fine. The two things can obviously minimize VFE independently. More interestingly, also, if they're kind of running in sequence, you can see this VFE as compositional as well. So in a slightly more subtle sense. So the idea is, because there's only this one output from O2 now, the observation is just on O2, so it's like at the top, it feeds in. So the second model, the one at the top of the composition, does its free energy minimization. And then the one at the bottom needs to receive some kind of observation for us to even make sense of it. But that would be given by sort of being passed down from the top one, so it would be given as the marginal of Q2 from up here. So you think of the kind of updating running down the diagram. So the O2 at the top is, updating happens to get a beliefs over this sort of middle wire, basically, which are then passed down to the lower model. And again, now this simply is given by just adding the two of them, and the way you prove it is just by some graphical rules that these log boxes satisfy. So you can prove this operation of drawing this green box around the effects to go from an effect to its negative logarithm, satisfy some nice graphical conditions, and then these just drop out from that. So before finishing, I'd like to talk about just what active inference is from give a sort of high-level view of it, putting some of these pieces together. So in active inference itself, at a level of abstraction, you can view it as applying to an agent with a model of this form. So it's like our discrete time model earlier, but just with two time steps at a certain high-level view of it. So we have this model where we have some observations happening now and some observations happening in the future. And we have a hidden state space for each. So O is the observations now, F the ones in the future, and S and S dash are the hidden states for each. And again, the agent's actions are at the bottom of the diagram, given by these policies. And what's happening is the agent's doing this kind of updating, but now it's got these two spaces observations. And what it's updating with respect to is an observation in the current time, like we've been talking about. And well, we can't see an observation in the future time because that hasn't happened yet. But what it has is some preferences about what it would like to see in the future, which are again modeled as a distribution. So it's basically updating for the special case where the model looks like this with respect to what's on the left here. So an observation in the current time and its preferences about the future here. And this whole notion of updating now is in the end going to just give us a distribution over P, these policies. We think of this as the agent planning its behavior. So it's got this observation about what's going on, it's trying to make sense of it. It's got what it would like to see in the future, and it's trying to choose a plan of action that would allow it to obtain what it wants in the future, that still makes sense from what it's seeing. So it wants to do this kind of updating, and if you look in the active inference books, you'll find a formula like this that they'll motivate in terms of the free energy principle, saying, okay, this is how it can do it. It's a sort of softmax expression involving some free energy quantities, the VFE we talked about, and this expected free energy, which I didn't mention yet. But the way this formula drops out, it doesn't drop out, it's sort of justified with a lot of words, and it's a little bit hard to see exactly where it's coming from if you follow the conventional approach. So we wanted to see how to get to something like this from just the structure of the generative model, so how to go from something diagrammatic to obtain this kind of formula. So I'll just sketch how that works, but I know I don't have too long. So roughly what I said is we're updating a model that involves these policies and these observations and preferences. And let's imagine we're doing this in a kind of Perl style update. So we ideally would compute this thing on the right where we plug the two on as effects and then normalize everything. So let's just take that thing that we would like to normalize. Just from the structure of what we know about the structure of the model that I showed earlier, we can rewrite this in terms of basically a part that's pertaining to the current time and the current observation, and a part to do with the future observation. And I've just called these both boxes M, but I mean, they are different things. They're just the part of M that relates to that. So we know that it happens to factorize in this way. And so we basically proceed in two steps. So you can look at this part that's relating to the current time and the current observation. And we do an approximation with this variation of free energy here. So you can basically show that carrying out this VFE minimization, this VFE update queue, but now it's done for every possible policy. So there's an input wire coming in here. So basically for each policy, we compute this VFE update, and you can show that multiplying it with this e to the minus of the VFE, e to the minus just comes from all these logarithms everywhere, will obtain an approximation to this, what's highlighted in the blue box here from before. This step, they call this the perception step, because it's doing this updating from observations to hidden states in the current time. Okay, so you start by doing that, and then we just take this top part of the diagram now that's relating to the future. Well, we collapse it together like this, and now we've got something that's just relating to future times and our preferences. And the part I didn't have time to talk about is this second free energy quantity called the expected free energy, but it's just given by plugging in another certain type of generative model into our general definition of free energy we gave. The point is that it gives you basically a bound and an approximation to this kind of thing. So this would sometimes be called a validity when you plug an effect into a distribution. So the agent can calculate this quantity known as the expected free energy to approximate this, or more precisely, e to the minus of the expected free energy would be the approximation. So we end up with a diagram looking like this. Obviously, you have to take my word for it on some of these steps, so we can talk about it in the questions if you like. And now we were saying that what we would like to do is just normalize this whole distribution, or normalize this to make it a distribution, and that would be our sort of plan of action. So if you then normalize this expression, you would get exactly the one that we were after, because there's these e to the minuses in there. The normalization ends up being this softmax expression in terms of the log, the VFE, and the EFE. So it's this formula that basically says there's a way the agent can do this kind of inference-style planning by calculating these quantities. So for each policy pi, so pi is sorry, I don't know if that was clear, but each pi is an element of P, so it's a specific policy it's interested in. And the distribution density over those is given by, for each one, seeing what our prior was, our habits, and calculating the VFE and the EFE in terms of those. And yeah, as I was saying, basically the thing that was nice was just seeing this kind of formula at least come out from something structural in the generative model rather than the slightly ad hoc way it's normally derived. So just to wrap up, the idea is that the sort of categorical probability style approach is really useful for clarifying lots of aspects of predictive processing and active inference. So we can talk about these open generative models. It's just the same way we talk about open causal models, and updating, as we already heard about earlier this week. And you can apply these to the special case in predictive processing to describe planning behavior, perception, and this active inference thing, and also to talk about compositionality of free energy. In future, some stuff we could do would be to look at how this free energy is actually minimized. So I just said that they minimize it here. The way it's actually done is with these algorithms called message passing that we didn't get into yet. And there's lots of interesting questions about these different notions of updating with respect to soft observations, and whether Pearl or Jeffrey updating have any particular, which are more natural when you're thinking about cognition and so on. And finally, it would be nice to tie this work all in with sort of more AI type things like this compositional intelligence program and other related work in categorical cybernetics. Thank you.
Do we have a short question for anyone?
This is really cool. It's great to see all this stuff really coming together to describe these kinds of short, sorry. So in the definition of free energy, you had this difference of logs. You could put that into a single log by taking a division. I wonder if there's an interpretation for that single quantity, which would be MSO divided by QS.
Yeah, I'm sure you could. Do you know anything about that, Toby? There's so many. Yeah.
I don't know. I can't remember which decomposition this one refers to. Sometimes there's like one term you could think of as like accuracy and one term as complexity. Sometimes you could think of them as like something to do with exploration and exploitation. It depends on how you factorize these things. But that particular ratio, I'll have to think about. But they all have interpretations.
Thank you. Put your hands together for Sean Tull.
Thank you.